Hi everybody, I wanted to try something a little bit new today. Wanted to share some comments on problem 3 of problem set 1. It came up in office hours and in a couple of discussions with students outside of class. One of the things that you got to understand in this class is that we really make the transition from the purpose of homework problems is no longer just to get the right answer. Very often the individual steps involved in solving some of these homework problems are going to be things that are going to come up frequently in lecture throughout the semester. So it's important that you really understand the process of solving the homework problems, not just sort of understand how to get from point A for point B. It's the mentality is more like in previous classes, it's like, okay, could I do this on an exam? The mentality here needs to be, I really want to understand the process better, because it's not just about getting points on an exam or homework, it's going to be about understanding what we're doing for the rest of the course. So in this problem, we're showing that this condition of mean independence implies that random variables have zero covariance. And if you remember what we talked about in class, it's sort of a hierarchy. If you remember what we talked about in class, you have independent random variables have covariance of 0 always, but zero covariance random variables aren't necessarily independent. Mean independence is sort of an intermediate step in the hierarchy where independent random variables are always mean independent. Mean independent random variables always have a covariance of 0, but you cannot necessarily go the other way. Covariance 0 random variables are not necessarily mean independent. Mean independent random variables are not necessarily fully independent. But the reason I'm giving you this problem is actually there are a couple of steps here that are related to things that we're going to be doing very frequently in class starting next week. So let's dive into this. What we're doing here is we're going to be showing covariance is equal to 0, and I'm giving you this hint that this is something from sort of the basic stats class that you might have seen, that the covariance between two random variables can be written as the expectation of their product minus the product of expectations, all right? So as we talked about in class, sort of oldest trick in the mathematical book, if two things are equal, then the difference between them is equal to 0. So if we can show that the expected value of the product x times y is equal to the product of the expected values, then we'll have that covariance is equal to 0. All right. And one of the sort of key things to understand about doing these derivations is it's not just about doing the algebraic manipulations, it's about understanding, because we're trying to understand an implication. We're trying to understand why this thing that we're assuming implies the given result. So this needs to show up, using this assumption needs to show up as a key step at some point in our derivation, and we're going to need to highlight exactly where that happens. So let's go ahead and start, because there are 3 steps here that are not just important to solving the problem, but are things that we're going to be doing in class. And the first is to apply the law of iterated expectations, okay? And so what I'm going to do is I'm actually going to apply the law of iterated expectations to the expected value x times y. I'm going to write the expected value of x times y as the expected value of the conditional mean expected value of xy given x, okay? And so this is the first sort of important lesson that we learn in doing this problem, and that is, notice that we did this when we did this in class, all right? The standard law of iterated expectations, as we stated it in class, states that the unconditional mean of any random variable y can always be written as the expected value of the conditional mean, where sometimes for clarity we put a subscript x on that outer e to emphasize that that outer expectation is being taken with respect to the distribution of x. So the first important thing that we learn in this problem is that you can apply the law of iterated expectations to anything. So we happen to be applying it here to the product x times y, not just to the random variable y itself. And that's going to be important. We can take and apply the law of iterated expectations with anything on the left of the bar or the right of the bar that we want. And we're going to be making liberal use of that in class next week. Okay, so let's get rid of those 2 so that we don't distract us as we're going on. All right, and now the second little insight here is going to be something related to the definition of conditional expectation that's also going to come up again next week, and actually over and over again as we move throughout the semester. And that is that according to the definition of the conditional expectation, taking the expectation of something conditional on X says we are treating whatever is on the right side of the bar as a fixed and known quantity. So we all know, for example, that the expected value of 5 times X is 5 times the random variable X. Because 5 is a fixed number, we can pull it out of an expected value, right? So expected value, I'll just write the side note here. We all know that the expected value of, say, 5 times the random variable X is 5 times E of X. You can pull fixed multiplicative factors out of conditional expectations, where this 5 looks a little bit too much like the letter S for me. There you go. The number 5. I feel like Sesame Street. This episode is brought to you by the letter S and the number 5. There you go. Okay. Here's the thing. Because X shows up on the right side of the bar in that expectation, we can pull this inner X outside of that conditional expectation exactly as if it were the number 5. Because that conditional expectation says take the expected value of whatever's on the left of the bar, treating whatever is on the right of the bar as fixed and known. So we can go ahead and just pull this inner X out and write this as the outer expected value of X times E of Y given X. Now you have to be a little bit careful, okay? You could not pull that X out of the outer expected value because there is no bar on that outer expected value. That outer expected value is not conditioning on anything. So you can't pull X out again. But as long as X is being conditioned on, as long as it's something to the right of the bar, anything to the right of the bar can be pulled out of a conditional expectation exactly as if it were a fixed and known multiplicative factor. That's the point. Okay. Now, here's where I was saying earlier, when you're doing these kind of derivations, you need to understand where is it that I'm using what I've assumed. Here's where we're going to use what we've assumed, because in this third step, we're going to now use the assumption of mean independence, okay? So under mean independence, the expected value of Y given X is always and everywhere equal to the expected Y. I have a tendency to make my tails on my Y a little bit short. Let's do that. That looks a little prettier, okay? And I actually, if you have a colored pen, if you have a highlighter, okay, I actually like to highlight, okay? Where exactly is it in my argument that I've used that central assumption? Because again, when I'm sort of looking back at this as what have I learned, all right, I want some sense of not just I pushed symbols around until I made something equal something else, but I want to get a sense of why what I'm assuming implies the result. And sort of understanding exactly where in the argument that central assumption gets used is a really important part of that. So there you go. That's where we needed to use that assumption. And now the very last thing is, once we get something to an unconditional expectation, once we get to an unconditional expected value, the unconditional mean of something is just a number. Okay, so when I take the expected value of any random variable X, whatever it is, that expected value is a fixed real number, and that can once again be pulled out of the expected value exactly like the number 5. Okay, it's important in order to do that, that needs to be an unconditional expected value, okay? So I couldn't just have done that in the previous step. I can't pull E of Y given X out because that's still a random variable. But once I get all the way down to an unconditional mean, once I've used that assumption, as we talked about a second ago, that E of Y is now a fixed number that I can pull out. And now once you realize that, you realize that once I've pulled E of Y out, X is the only thing left under that E that we started with. And so this does become the expected value of X times the expected value of Y, and we're done. Because we now started with expected value of X given Y, we've shown that under the assumption of mean independence, that that is always equal to the product of the expected values, and therefore we know that mean independent random variables will always have a covariance of 0. And it's really important, again, I'm not just giving you this problem so that you push symbols around. I'm giving you this problem because this step here in particular, pulling something on the right of the bar out of an inner conditional expectation, and as well as the idea that I can use the law of iterated expectations with anything on the left or the right of the bar as I want. Those are things that we're going to be using quite extensively over and over again in class throughout the semester. So those are things that you're going to need to think about and understand. Okay, so I hope some of you, for some of you that this helps to understand sort of the context of the problem, and I hope that if some of the explanations were a little bit all over the place, that you'll go back and sort of do the problem again and think about it with this in mind. This is something, I get asked a lot in this class about, oh, can I get extra practice problems? Guys, for my money, most of the time, the best extra practice problems is to take a problem that you've already worked and work through it again. Think about how you would explain it to somebody else. Work through it in a group and ask each other questions about the individual steps and sort of try to understand the process, because again, the goal of homework in this class is to understand the problem solving process, not just to get the right answer. Thanks for your attention, and I hope you guys find this useful.